The things that we discussed in last class. Oh, okay. Now let me share this screen. Is this screen visible? So now, so here, what we discussed in last class was um, this is stack. So if we talk about a stack, so stack follows last in, first out. So now let's say I have created a list. Okay, this is linked list. This is first node. This is second node. This is third node, and last node is null. So what's happened is this in this list, this is the element that is coming at first. Then this will come. Then this will come. Okay. So means in both way you can do. So here in case of linked list now last in first out. So this is the third element that has been inserted, right? So as soon when push operation will come, push operation refers to insert a new element. Okay. Then whenever the pop operation comes, pop operation confirms that we have to remove an element. Okay. Now the step follows like this is the structure is there, and so in this stack what will happen, this is null, so this will be the element that will be coming at first level, then this will be the, so as soon the first element comes, what will happen, this element will be treated as top. Okay, but as soon the second element come, this top will move from here to here. Now this will be top. No, and this is not top anymore. Okay, when third element has come, at third element, now top will come at here, and this will not be top anymore. So now top is here. So wherever a new element will come, top will refer to that. Okay, so whenever we push an element, so push element will be will be pushed at top only, right? Because top is no, right now the top is the element which was last inserted into this list. Okay. So whenever a new element will come, it will be coming at the top only. So let's suppose fourth element comes, so fourth element will automatically come at this position. Top will move from here to here, and this will not be top anymore. Okay,
Okay.
so like this it will work. So what it, from linked list point of view, what it follows as that element is what we are following for insert at start. That function will be followed over here. Okay. Now when we say pop an element means remove element from stack. Okay, and now stack follows last in first out. Now this is the fourth element that has come at last, so only this is the only element which will go at first. So when the element will be removed, so when this will be removed, this top will move from here to here, this will be top, and this will not be top anymore. Okay. Then when again if we say pop an element, so this top will go from here to here, top will be here, this will not be top anymore. So you can see The fourth element was the element which was inserted at the last, and that has only been popped out first. And then second was third. So whenever we say pop an element from the stack, so we will for from linked list language remove element from the start. Okay.
So, so popping an element, if you want to pop, can we pop any element from the list?
No, no. You now here are the restrictions. You cannot do that. You cannot pop any element now. Here
Hmm?
it is the location sensitive. The stack and queues are the location sensitive.
So we can only pop the last element, and we can insert only on the top.
You can insert only at the start, and you can remove only from the start. So where you are inserting, from there only you have to remove.
Okay.
Okay.
Mm-hmm.
So this is what is the stack that we are going to implement in our code. Okay.
Okay. Mm-hmm.
So now let me share this other screen. Okay. So now here also you can see what I have done is here in this case I have taken just now you can see I don't have any option in the inserting or deleting. I don't have any option to insert at start or insert at last. I don't have any such options now. Okay.
Mm-hmm.
So
Yeah,
here
only this number.
here it is pushing the number, and here option insert is not this is not required now.
Can
This
you
is
please explain the coding?
yes, yes. I'll explain. Don't worry.
Mm-hmm.
I'll explain everything. Just so here what I'm doing is first of all I'm taking two number that are to be pushed. Now what I am doing is node one, and at node one I am taking a one number, and at node two I am taking second number. Now what I'm doing is node two of next is equal to node one. Okay. And then top is being moved at node 2 at this position, right? Now when here I'll take, suppose a push operation is taken, so at push operation I'll pass as top over here. Okay, and here also I'm storing top everywhere. Now inserted in, instead of node 1, top will be there, because from top only we at top only we are inserting an element, and at top only we are removing an element. Okay, so everywhere top will take place now. Okay, so let me execute, and let me see what's happening, then I'll explain it again.
Okay.
um so first of all let me, yeah, this is executed. Okay, node 1 unexpected indent. Where it is put. Okay, sorry, here this indentation is not required. Hmm. Hmm. So first number I'm taking 34, and second number I'm taking 67. Right. So now you can see 67 is at top, and then 34 is there. Now I am pushing an element. So I am taking option as one. So which the element that I want to push, let's suppose I want to push 45. So 45 is not pushed. Yeah, so something I have to do for this. There should be some changes in the code. So I don't want to push anymore. I don't want to process anymore. So let me see what it is doing is print is stack. Uh, this is taken nd. Okay, here only also I have to do top. Yes, now it will do. And here also. Everywhere at node 1, I have to change it at top. Okay, so now again 45 and 90. I'll take push and here I'll just insert 23. Okay, so see 23 is inserted. Okay, I want to push more. 78, 78 is inserted. I don't want to push anymore. I want to process more. I want to do the pop. So as soon I did pop, you can see here 78 is automatically, 78 was the first element. It is removed now.
Okay.
Okay. Then again, if I want to pop, so just I'll do pop yes. So it will immediately perform the pop operation and it will show this that first element is removed. So earlier 78 was removed, then now 23 was removed, now 90 and 45 are there. Okay, now I don't want to pop anymore, so no. And I want to process more, yes. I want to display, so my stack is this. Okay,
Mm.
so ultimately what I'm doing is simply if any number is to be pushed, that number will be pushed at the start. So here it is the push element, and here top is
So
coming in.
top is the keyword.
Sorry,
Top is the keyword.
top is the location of the element where
That,
the element needs to be pushed or popped.
oh, you have mentioned top is equal to node 2.
Yes.
Okay, so okay, we can do it for the queue. We can mention last, right?
Yes, for queue means I'll explain you the logic of the queue as well, so
Mm-hmm.
that you can understand that. So here the stack follows last in first out. Okay. In
Mm-hmm.
case of queue, it will follow first in last out. Sorry, first in first out. Okay. So I'll share this other screen and I'll show you diagrammatically.
Mm-hmm.
So it will be very easy once you have done one program by yourself. It will be very easy for you. Okay.
Okay.
Okay. So this now the queue will be queue follows queue follows first in first out. So for example, you have a tunnel is there. Okay, in this tunnel, somebody there is a line. Okay, so person are coming from here and person are going out from here. So the person who has entered in this queue first, that person will go out at first, and the person who have entered at last will go out at last.
Mm-hmm.
So this is first in first out and last in last out, FIFO or LILO, whatever you want to say. First in first out or last in last out. Okay,
Okay.
so in this case what you will do is when you will make a program, it will be very easy. When you will make a program, so like you have created nodes, four nodes like this. So here this is null. Okay, so here what you have to do is here you have to use this front and rear. Okay,
Mm.
front node and rear node. So rear node is the last node and front node is the first node.
Person.
So
Mm.
so now how now first of all, this first node is taking place. Okay. After that, this second node is taking place. After that, this third node is taking place. And after that, this fourth node is taking place. So like that, no, this all processes doing. Now, this is the insertion process. So first of all, when this first element will come. After that, the second, then third, then fourth. Now, when there will be a point of deletion, so the this is the first element which came at first, so now this element only will go out first. Okay,
Mm-hmm.
now when this element will go out, this front will be moved from this place to this place. Now this will be the front. Now when you want to remove an element from this front will go out, and this front will be moved from here to here. Okay, so here element will come and here element will go out. So this is the place to insert and this is the place to remove. Okay,
Mm-hmm.
so in linked list point of view, so in linked list point of view, to insert, what we have to do is insert at last. And for removal point of view, if you will see removal point of view, we will remove from start. Okay,
Mm-hmm.
so you cannot remove anything from any certain position.
Okay.
Okay,
Mm-hmm.
will you be able to make this program by yourself, or should I make it?
Okay, I can make it by myself. I'll try today. If it is not working out, I'll let you know tomorrow. So
It
we
is
can.
very it is very easy, and just you have to try it. Means all the functions are already you have made in linked list somewhere,
Okay.
right? Just you have to give the limitation. You can see linked list can do everything. It can insert anywhere, it can remove from anywhere, it can undo anything, right? But
Yes.
stack and queues are just the limitation of the linked list.
Okay.
Linked list with limited operations means now you cannot insert anywhere or you cannot remove from anywhere. And in
Mm-hmm.
stack, you can insert at start and remove at a start. And in queue, you can insert at last and remove from a start. That's it.
Okay.
Okay, so according to that, you have to make choice. You have to select those functions and you have to keep them only
Okay.
in code. So you can see how small code this is. The linked list code was very big. You can see that.
Yes. Yes, I can see. Yeah, can you please share me the code for stack?
Sure, I'll share this code.
I'll,
Shall I share just by um, this code directly to group?
anywhere like Notepad or group. Any group is good. Yeah.
I am pasting the code entirely in group only, directly in group.
Mm-hmm.
Okay, so I have pasted the entire code in the group directly.
Okay.
Okay, this is very small code. So in the same way, you can make your own code of the queue also.
Okay. Will
Okay,
do. Yeah.
clear?
Sure.
Okay. Next, now we are going to study about the trees. So let me open a new page. So now, till now, we were studying about the array and linked list. So these two were the linear data structures. Okay.
Mm-hmm.
Now we are going to study about trees. So when we talk about the trees is nothing but it is a binary data structure. Binary data structure. So how this follows is you have one element over here, and at the left you have one element and at the right you have another element. Now this node is known as the parent node, and these two nodes are named as children. Okay, or you can say this is as root and this is at leaves. Okay,
Mhm.
understood.
Yes.
So now these children can also have their own children, right? So this can be extended like this, and then further can be extended like this. Okay, so these
Mhm.
things can be extended further as well. So this is a overall binary tree. Okay, understood. So where
Mhm.
we have only two children, that is known as binary tree. Now there is a simplification concept comes in. This is that is binary search tree. So binary search tree is called as BST, binary search tree. Okay, so in binary search tree, we have identification. Like first of all, if suppose you have few numbers like I want to insert five six numbers in the tree. So let's see. I am taking 20, then I am taking 35, I am taking 15, I am taking 12, I am taking 14, and I am taking, let's say, 20, um, 26 and 38 I am taking, and 24 I am taking. Like this I am taking. Okay, so let us insert this one by one. So first of all, when 20 will come into the binary search tree, 20 will be the first node. This is the initial node. Now what binary search does is, binary search means right is greater than root and left is smaller than root node. Okay, so right now this is the root node, right? So what we'll do is 20 will come, and now 35 will come. 35 is bigger than this, so 35 will come at the right of this. So this will come over here. When 15 will come, 15 is smaller than root, so 15 will come over here. Now next 12 is coming. So 12 will be first compared with the 20. So it is smaller, it will come to 15. 15, say it is still smaller than 15. So it will come at over here. Now next 14. So it will be compared with 20 is smaller, 15 is smaller, 12 bigger. So now this will be at the right of this. Okay. Now next is 26. So 20 is smaller than 26, so it will come at right. 26 is smaller than 35, so at left this 26 will come. Okay. Now 38. So 38 will be compared with this 20. It is bigger, so 35 is also smaller, then 38 will come over here. Okay, in the same way 24 will come over here. So you can see here at every stage, you can see the the right node is bigger than its parent node. Okay, its root node, right node is bigger, and left node is smaller than that.
Mhm.
Okay.
Yes. Mhm.
Understood. Understood. So now let's suppose somebody says that I want to search an element in this list. So somebody says that 30 I want to search over here, right? So when 30 will be searched, so immediately 30 will be first of all compared with 20. So now since 30 is bigger than 20, it will not even go at the left of this to search this 30 node because it is bigger, so it cannot exist at the left side. So it will come to 35. Now 35 is bigger, so it will come at left of 35 because it cannot exist on the right of 35. Now it will be compared with 26, right? So now 26 is smaller than 30, so it will come at right. So there is no right of 26. It means now 30 does not exist in the tree. We can say just by three comparisons, right? So normally, if I have to search, what I have to do, I have first I'll compare with 20, then compare with 35, then 15, then 12, then 14, then 26, then 38, then 24. Like this, I have to do eight comparisons. But now here in just three comparisons, I got to know that this element does not exist. Okay.
Mm-hmm.
Understood. So this is what is the benefit of binary search tree is that the searching becomes very much effective and faster.
Okay.
Okay, and
Mm-hmm.
with very few comparisons, you can declare whether the element exists or element do not exist.
Mm-hmm.
Okay. So
Okay.
now we have so the data structure for binary search tree is basically it is defined in three parts. So one part is the number itself. Other two parts are for the locations. Okay, so we'll define as class tree over here, and it will be defined as defined double underscore init double underscore self comma data. Okay, then self dot data. Right now, there will be just data in this, and then self dot left is equal to none, and self dot right is equal to none. So these two positions are the left and right nodes. Okay,
Okay.
okay.
Mm-hmm.
So like this, you can create the tree. So we'll discuss the algorithm of this, how to when numbers are given, how we'll create the list. We'll do that. But here to display these elements, we require some arrangement. So there are three kind of arrangements are there to display these elements. So in that, one is pre-order, number two is in order, and number three is post order. Okay. Do you remember something that you studied during your engineering?
So I remember this binary search tree, but this pre-order, in-order, post-order, I don't. This
Really?
parent child, I remember binary search tree, I remember, but I don't know what is pre-order, in-order, post-order. Maybe after you explain.
Without knowing pre-order, in order, post order, how can you print the elements in the binary search tree?
Mm.
There is no other way of printing.
Okay. Mm-hmm.
Okay. So now what is pre-order? So in pre-order, first of all, we'll print root node, then left node, and then right node. In order, we'll take first left, then root, and then right node. And in post order, we print first left, then right, and then root node. Okay.
Mm-hmm.
So now see we have already created this um, tree. So now if I want to print it in let's say I want to print them in print it in pre-order and in order and post order. So how it will look like? So in pre-order, first of all, we print the root. Okay, so this is 20. Then we'll print the left side of it. So will from 20 will come to 15. So it will come at 15. Then from 15 will come to left side of it. So 12. Now 12 left of 12. So there is no left of 12. Then we'll go to right of 12. So we'll come at right of 12. So this is 14. So this is 14. Okay. Now when all the when on these four are printed, Now, what we can do is next, left of this entire 20 is printed. Now we'll go to the right of 20. So right of 20 will be 35. Then left of 35, 26. Left of 26, 24. Now there is no right of 24. There is no right of 26. Now it will go to the right of 35. So 38. So this is how it is printed in pre-order. Okay.
Okay.
Now, if we will print in the in order, so if we print in order, so first of all left, then root, then right. So left is right now uh, root root of left 15, 15 of left 12. There is no left of 12, so we'll print 12 first, then right of 12. Then we'll go back to the 15, then 20, then 35, the left of 35, 26, left of 26 is 24. So 24, no right of 24, so we'll go back to 26, then we'll go back to 35 and then 38. Okay. And in the same way, if we talk about the post order, so first of all, left and right will be printed, then root will come. Okay. So 20 left, 15 left, 12, no left of 12, then right of 12. So 14 will come first, then 12 will come, then 15, then 24, then 30, then 26. 26, then 38, then 35, and then 20. And understood this is somewhat 50%.
Mhm. Yes.
How this is working? So you can observe over here is that root node in pre-order is the first number. Root node in post order is the last number.
Mm-hmm. Mm.
Okay. And here it is somewhere in middle. You cannot say it is exactly in middle. It is somewhere in middle. Okay.
Mm-hmm.
So if suppose someone says that this is a post order of a binary search tree. This is a post order of binary search tree. So what is the root node of binary search tree? You can tell easily. Okay.
I okay.
Okay. So just by seeing at last node in the post order, you can find out what is the um, root of this tree. Okay, in order you cannot identify a root of this tree directly. You cannot identify in order.
Mm. Okay.
Okay, but
Yes.
in case of pre-order and post-order, you can easily identify the root of any binary search tree.
Yes.
Is this clear?
Yes.
Okay, so now when you will be inserting a new element in the binary search tree, what you have to do is again you have to take element and you have to print them. You have to arrange them as by searching. So up now in this tree itself, suppose somebody says that I have to insert a new element as let's say 29 if he want to insert a new element into this tree. So how it will be inserted? So first of all 29 will be compared. So like in linked list you have the starting element. In the tree you have the address of just root element. Okay.
Mm.
So the 29 will be compared with the root first. Okay. If it is smaller, then root the temporary element will go at the left side. If it is bigger, temporary element will go at the right side. Now, so first of all, this will be compared. So how this will look like? First of all, temp is equal to root. It will be the first statement, and then it will be compared if temp of data is greater than um, um, is greater than the new of data.
Okay.
Okay,
New. Mm.
if it is greater, then what it will do is, um, since temp of data is greater, it means new data will go at the left of this. So temp is equal to temp of left.
Mm.
If this condition is false, so this is the if condition. If this condition is false, it will be compared with as temp of data is less than new of data. To add that case, new element will go at the right. So temp will be moved at right. So temp is equal to temp of right.
Right. Right.
Okay.
Mm.
And if these both conditions are false, the element is neither small, neither bigger. It means this is a duplicate element. So simply it has to print the message that duplicate element. Okay.
Okay.
So like this, when this entire thing, the entire operation will be performed.
Okay.
Any doubt in this?
I'm good. I'm good. I think I'm good.
Okay, great. BS.
Left, right, root, root, prayer, post. No. Okay.
Do you have any doubt? Any confusion?
No, Kushal, I'm good. Yeah, it looks not much serious. But I have to.
Getting confused?
No, no, I'm not getting confused. It's clear only. Um.
Okay.
mm,
So this will be this will be what kind of operation I can say? This is the basically more of the searching operations are involved in this. And as soon as searching gets finished, then you will be able to insert that node into the linked list. Okay, in the same way, when now, so let me tell you the scenario of the deletion as well. Then we'll move forward towards the coding. So this is the scenario for inserting a node into the binary search tree. Okay,
mm,
now now we'll move to how to if someone say to delete an element. Okay, so delete a node in binary search tree. So in to delete a node in binary search tree, simply again somebody will say that this is the element that has to be deleted. Means an element will be given from the user side to delete an element. Okay.
mm-hmm.
So now again the searching operation will be performed. Okay. So now when searching operation is performed, so you can see there can be the multiple scenario. Now somebody says that I have to delete um, 14 in this. Okay. Or somebody says that I have to delete 26 in this, or somebody says I have to delete 35. So there can be three kind of scenarios. So you can see in one scenario when 14 is there, so 14 has no child in it.
Yes.
Okay. No left, no right. When I
Mm,
say I have to delete 26, it has only one child.
mm,
Okay, so it has only left child. In the same way, there can be only right child also. And the third scenario, when the tree has both child, left and right, both childs are there. Understood?
yes.
Understood the situation? These three circumstances, one is left child. When is there is no child, then another scenario is it has only left child or it has only right child, or third scenario when it has both child.
Okay.
Okay, just
Mm-hmm.
try to observe. I don't expect you to understand it everything in one go. Okay, so let me make this tree again. 20, 15, 35. I'll make it here. 20, 15, 35, and 12, 14, 26, 38. This is 12. This is 14. This is 26, 20.
No, the 12 should be connected to 14.
Yeah, sorry.
Then 26, 24. 26 after 24.
This is 24.
Yes,
This
24.
is it. Okay, so now let's suppose I have this is the root node. This is the root node. Now I have to delete first in first scenario, delete 24. No, not 24, 14 I am taking.
Mm.
Okay, I'll take 14, delete 14, 14. So in this scenario, node has no child. When node has no child, what you have to do simply is simply so this is the node to be deleted. So I'm supposing that this is a temp node. So what I have to do is this is the parent of temp. Okay. Okay.
Mm.
So in this case, what we'll do is if this is a right child, so you have to check whether um, means first thing is this first thing is it has no child. Second thing you have to check whether temp is left child of its parent or it is right child of its parent. Okay, whether temp is left child of its parent or right child of its parent. Okay,
Mm.
so in this case, 14 is the right child of its parent. So in at third stage, you have to do is like parent of right is equal to null. Okay, so as soon you will do this link will be broken and this will be out of scenario. Okay,
Mm-hmm.
understood?
Yes.
Then second case can be the tree can have either left child or right child. So let's say I am deleting delete 26. So in case of this node
Parent
has
of left is equal to no. Oh, no. It's
one
parent of left.
one left child. Okay, node has one left child.
Left
So
side.
yeah. So node has one left child. So at this case, what what we'll do is now when 26 will go, so 26 is 26 left child is 24. So the child of means anything after this 26
Mm.
will always be smaller than 35.
Yes.
Anything after this 26 will always be smaller than 35. Okay,
Yes.
so let's say if 24 is there or if 24 is not there, then instead of 24 there is 29. So whatever, either 29 or 24, both will come at the left of this 35,
Five. Yeah.
right? So what now we will do is, so now this is the temp node and this is the parent node. Now in this case, um,
So you wait. Let me tell you.
yes,
So now we are going to connect this parent. No, the temp of left node is equal to the parent of the
yes.
left
So parent of left is equal to temp
to
of
left.
left. Okay, and
Mm-hmm.
And if suppose there is 29 is there, right?
The same
So
thing.
just assume if this is not there, instead of this is there, 29 is there. So at that case, parent of left is equal to temp of right.
Mm-hmm.
Okay.
Yes. Mm-hmm.
So in this case, this also will get connected over here.
Okay.
Okay.
Mm-hmm.
Understood this scenario?
Yes.
Very clear?
Not very clear. Clear.
Okay, no issues. I don't expect 100% to absorb over this
Yes,
time.
I can
I,
understand. Yeah, if I see it one more time, I can.
so
Yeah.
when we'll do the coding, all these things will be repeated again. Don't worry.
Okay.
Okay. Now the third scenario is now let me draw this whole again. So this is 20, 15, 12, 14, and then here at right side we have 35, we have 26, we have, let's say 29 I am making over here, and 38. Now what I want to do is I want to remove this 35. Okay, so I am deleting, delete 35. Okay, so when I am going to delete 35, so here node has both left and right child. Okay,
Okay.
understood?
Mm-hmm.
So at this case, what we'll do is we have to find a minimum value. Okay. So
Mm-hmm.
now since I have to I have to do I have to delete this 35. Okay. So now what I have to do is I have to find either of one thing, means you can find
Mm-hmm.
you try to find number one, um, smallest element of left subtree or biggest element of right subtree. Oh, sorry. The smallest element of right subtree, the smallest element of right subtree, or biggest element of left subtree. Okay, any of these two values you have to find, either the first one or second one. So what I mean to say is that let's suppose I have to delete 35. So now what will be done is, one thing is that 38 will come here. Okay,
Mm-hmm.
30 38 will come here, and 26 and 29 will be at the left of this. Okay, so here after deleting 35, we will be having scenario like 20, then 38, then 26 and 29. Will have scenario like this. At the right side, left will be as it is.
Mm-hmm.
Okay, so this will be 15, 12, 14. It will be as it is, and at the right side will have scenario like this, or we can have also the scenario like 20. Left will be as it is, 15, 12, and 14, and here it will be 29, 26, and 38. This scenario also looks fine,
Mm-hmm.
right? So
Yes.
now just to relate. So smallest element of right subtree. So 35 right subtree is 38, just this one element. So biggest or smallest, this is the only element. So this is the element which we can bring back to 35, or the biggest element of right subtree. So 29 is the biggest element of right subtree. So this also can come at the place of 35, and 38 can be right off at the right of this. Okay.
I don't get it. See, you have if the 35 is got deleted, the 38 goes in the right side of 20, right?
Hmm.
And then
Okay.
the 20, 28, 29 comes down. That's fine. What is
Hmm.
this 29? Why the 29 comes in after 20?
Both scenarios are possible. See, you if you place 29 over here, does it break any rule of binary search tree? Is it breaking the rule of binary search tree? No.
No, but you
Huh.
know the biggest. Yes, no,
Yeah.
no.
Let me tell you the challenge now, why you are not able to see this. So let me
Mm-hmm.
take another example. So I have tree, uh, 20, 15. This is very important to understand. Don't worry, you will
Mm-hmm.
understand. So here I have right now, this is there 35, and this is 26. This was 29. Correct? This side I am changing. Just I am writing 38 over here, and here I am writing, let's say, 37, and here I am writing, let's say, 45. Okay. Now, if I am deleting this 35, which element?
So my question is here. Let me stop you here. So you see, my if we are doing the binary search tree, so the bigger number comes at the down, and then the less than that number comes on the top. Likewise, it goes right. That is how we have created the tree. 35, 38, and then 26, 24. Likewise, only we have created the tree, right?
Yes, yes.
Anyway, so can I consider like anyway, like you're showing is possible? It can be also be like this.
Mm, I didn't understand your question. Can you please repeat?
So can you please scroll up where
Hmm.
we have created the binary search tree?
Hmm.
So it comes in the order, like it comes in the descending order. See, if you
It's
see here, 35, 30, 38, above 35. In this side, 24, 26, 35.
hmm. So, is this order breaking over here and at any point? Left should be the smaller and right should be the greater. Is this any of that thing is breaking over here?
No, but 29, like 29, 30, 26, 24. Can you go scroll down? Here you have written 35. Mm-hmm. Okay, I don't
So
think so.
this is binary search tree, correct?
Mm-hmm. Yes,
At the
yes.
right, it is bigger, and at the left is smaller. At every node, you can check. Right is bigger and left is smaller. Okay.
Mm-hmm.
Now, what I now the challenge with us is we have to remove 35, right? And
Mm-hmm.
now at the place of 35, what should come?
So let me come to the point.
Hmm.
So 38, the 45, 38, 38, 35. Okay, this is correct. Oh, okay, okay, got it.
Okay, so now
Mm-hmm.
now the challenge with us is that what should come at the 30 at 35. Now, for example, if I take 29 at if I take this over here, 29 over here, so 20 so at the left of 26, 29 cannot come, right?
Mm-hmm.
And if I take 38 over here, then at the right of 38, 37 cannot come,
Mm-hmm.
right? So we have challenge. So for this challenge, what the solution is what we wrote over here. We have to select any one of element, the smallest element of right subtree or biggest element of left subtree. So smallest element of right subtree. So here right subtree is this. This is the right subtree.
Mm-hmm.
Okay. So the smallest element of right subtree is the leftmost element of this subtree.
Mm-hmm.
So we can use this. Okay.
Mm-hmm.
So if I place 37 over here and I remove 37 from here, do you see any point breaking?
No, no, it
Uh,
is not.
right. In the same way, the biggest element from the right subtree. So biggest element of left subtree. So the left subtree is this. Left subtree is, let me point with another pen. So this is the left subtree. And this is the biggest element of the left subtree.
Yes.
So if I place 29 over here, do you see any point breaking? Any rule breaking?
No.
Okay, so any of these two we can do. Either we can place the smallest element of right subtree or biggest element of left subtree. So any of this we can do. So after this, our result will be um, 20. Then in the right subtree, it can be right like 37. At the left, there will be 26 and 29, and at the right there will be 38 and 45, and 35 will be removed from here, or it can also be like 20, or 29 will come here and 26 will be here as it is, then 38 and 37 and 45. So any of this can be solution in this case.
Okay.
Understood?
Mm.
Just try to visualize this in your mind so that you can understand what actually is going on.
Okay.
Okay,
Mm-hmm.
so understood all three scenarios. One is it has no child, another one it has either left child or right child, or another one it has both child.
Yeah.
Okay,
Mm.
any doubt in this?
I'm good.
Okay, so tomorrow we'll do the coding for this.
Okay.
So this everything will be revised again.
Okay.
Okay, so you will be clear with this.
Okay.
Okay,
Okay, Kushal. Yeah.
okay, thank you.
So I have one question.
Yes,
So
please.
once we are done with this, we are done with DSA.
Yes, although there are more topics are there, but I am not going to those topics in those details. If that requires in future, I'll take those topics in future. Okay.
Okay.
So
Okay.
there are
Fine.
three more topics are there, like graph is there, hashing is there, and heap is there. Three more topics are there. I'll not take that right now. Once this tree finished, after that, I'll start directly with the cloud part.
Okay. Okay, Kushal. Thank you.
Thanks.
Bye.
Bye.